All right. So last night, yesterday, maybe this morning, who knows when. In theory, we're continuing to work on 2.2, doing problems 29 through 48. I made a late addendum to the assignment yesterday and cut out 43 through 46 because we didn't really talk about that principle. Um, at the end of going over these answers, explaining them a little bit, um, I will do an extra, 5 minutes, just kind of explaining that whole principle for those of you who are interested. Obviously, for those going on to calculus, it wouldn't hurt you to hear at all, especially if you're heading to BC. But for the rest of you, you won't be tested on that idea. Um, so 43 through 46, you don't have to worry about too much. Obviously, these answers were there. I hope you are using these answers and in some cases full solutions to check your progress and see how you're doing so you know when to ask questions or not. I didn't have a single question on this submitted, so it makes it hard for me to have direction on what problems to spend more time on or what you really need. So I'm just going to kind of pick a couple problems here, maybe a problem or so there, and hope that that helps you out. 29 through 30 were some matching problems using end behavior models, which we used a whole bunch back in Unit 1, and rational functions, right? So one of the principles we learned yesterday is that the um, the lead power term of a polynomial, the the term that gives it its degree. We like to call it the lead term because in standard notation of descending exponents, it should be the first term, but sometimes it's not. For example, there's a couple in here where they didn't do it right. Not the first term that's the lead term, but in these cases, those two cases, the second. Um, so that power term is going to dictate the end behavior of the polynomial, and in fact, the further out you go, the closer they will become. Um, so, with that in mind, with rational functions, we just have to basically make a fraction with those two lead terms. And so for 29, that becomes 2x cubed, right, over x, which reduces to x squared. Well, that's just a parabola, okay? Maybe I guess technically it would be 2x squared, wouldn't it? But yeah, which one of these looks like 2x squared? Probably A, the up polynomial function. Number 30, x to the fifth over 2x squared, and that reduces to x cubed over 2. So what does x cubed look like? X cubic function kind of has that look. Well, that would be a linear function, kind of like that, right? So which of these has that down up behavior? It looks like C does, doesn't it? C. And then that means B and D have to go to 31 and 32 respectively. Um, 31 is 2x to the fourth over negative x. Don't put it over 2 because x is more powerful than 2. And so that reduces to a negative 2x cubed. So a negative cubic. So that's going to have the exact opposite, right, shape. And looks like that up down end behavior is D. And by process of elimination, I guess you don't really have to do 32 to get B. However, if you did, you would find that x to the fourth over negative x squared, right, is negative x squared. And so it would behave like a negative parabola, which is what B did. So there you go. Hopefully that makes sense. It seemed more like review than new material. The next set, 33 through 38, continue to explore this concept of power terms for polynomial and rational functions. All right, I believe it asks you for what the end behavior model, or I guess they called it the power function would be, as well as if there were any horizontal asymptotes. A couple of them had horizontal asymptotes, and most of them did not. So here are those problems, and just to take a quick look. First of all, what is a power function? A power function is where you take a single polynomial term, and um, and so it'll have possibly a coefficient A, right? Now, even if I guess it doesn't have one, if it's not showing, then it would be one. It would be one. It should have a variable, or it doesn't really count, and then it should have a positive integer exponent n. So that's called a power function. Your calculators have power function regression built into them. Um, at lower levels, they will do an entire like quadratic or cubic equation, but after that, they really just do power functions. But the power functions can get pretty powerful. Now, what our lesson yesterday taught us is that for any polynomial, the most powerful term in that polynomial, okay, will model the end behavior of the entire polynomial, because the further out you go, basically, uh, this stuff just becomes less and less of a factor. It becomes almost microscopically tiny by the time you get way, way out. And so that's what pulls the original function and the end behavior model together as we approach positive or negative infinity. Okay. Now the cool thing about polynomials, what makes them so darn simple, is that the power function end behavior model is going to work in both directions. So, in this case, your power function and behavior model is just y equals 3x squared. That's the answer is told us, and that's going to be true in both directions. It's just kind of like the matching problems we were just looking at. Okay. Now with the rational functions, and I'll just pick one at random here. Now you have to pay attention to the top and the bottom. In fact, you know what? Just because you're my friends, I'll pick three because these all have different outcomes. These are the different outcomes that we saw in the examples yesterday. The first one has a more powerful denominator, so the power function would be x over 2x squared, or 1 half, or 1 half x, 1 over 2x, I guess is the way I should say that. And 1 over 2x is like one of our infamous rational functions. It would look like this. Okay, and 1 over 2x would look like that. And so what is the end behavior model to that? Well, it's just 2 over x is the power function or end behavior model. What's the asymptote? Well, it looks like it's approaching 0 in both directions. So y equals 0 would be your horizontal asymptote for number 35. Now, another possibility is like 37. Now, 37, instead of the bottom, the denominator being more powerful, the top is, and that's going to behave just like a polynomial if you go far enough out. In fact, this one would be 4x squared, right? 4x cubed over x would become 4x squared. Y equals 4x squared. Wow, I can't write today. That would be your power function. So it's gonna behave like this, which obviously means there are no horizontal asymptotes. Anytime the top is more powerful than the bottom, right? The horizontal asymptotes. It's a diverging graph. In this one, because it's positive x squared end behavior model, would be up. And then finally, 36 is that case where we actually have a tie, right? X squared ties x squared. And so now all that happens is you take the remaining coefficients, which would be a 3 and a 1. There's nothing there, right? So that we would call that a 1. And 3 over 1 is 3. So what that means is if you graph this, it would just be a horizontal line at 3. So yeah, that would be a horizontal asymptote. It would be approaching is y equals 3. So that's the story on this section. And once again, it should have seemed a lot like review, because we talked so much about end behavior types for polynomials back in Unit 1, as well as end behavior and whether or not there are horizontal asymptotes for rational functions. So that takes us to the big problems, okay? Problems 39 through 42 were the problems that probably should have taken you by, about half the time of the entire assignment. And when you first start doing these, I totally get if it's a little confusing, but it's a pattern. And if you do them uh, enough, if you do a couple of them, you start to get into this rhythm, and then you just kind of get how it works. Okay, so here's the idea. Let's start with 39. I mean, it's all worked out for us here already, but I want you to think about how we would set it up. Okay. The first thing we need to do is figure out what we think is going to be the end behavior model in the left direction and in the right direction. And so to really understand that, we need to think of the two functions that are primarily in question. The original function for this problem was y equals e to the x minus 2x. And we can look at that in a second, but um, e to the x is one possible power function, or end behavior model, I should say, and negative 2x. You could rewrite that as plus negative 2x if you wanted to think of it more like that, but negative 2x would be, the other one. So we know what negative 2x looks like. That's just a line, right? That's just a line that kind of looks like that. And it's pretty easy to um, understand how its behavior is going to be. Now, e to the x, we're going to have to remember our parent function behavior, parent function shapes. So this is where, if you did well in Unit 1, it's really going to pay off in Unit 3. And if you struggled in Unit 1 or didn't really get your stuff down, it's not. Any exponential function really kind of has the same shape as long as you have a positive exponent, and e to the x is no exception. It kind of looks like this. So here's what we need to decide. Who's more powerful as we move to the left, and who's more powerful as we move to the right? Well, as we move to the left, e to the x is collapsing to 0, whereas negative 2x is slowly but steadily moving towards positive infinity. My the way I read this is that negative 2x is going to be the left end behavior model, and that's why we decided to divide this by it to check that out. Okay, now if you're like, why would we do that? This goes back to our discussion yesterday on the definition of an end behavior model. If you divide your original function by your uh, end behavior model, right? Depending on if it's a right or a left end behavior model, would be approaching positive or negative infinity, but that would have to have a limit as we move further and further to the ends of this graph of 1 for this to actually be the end behavior model. Because if it's an end behavior model, what we're saying is the further out we go, the closer these functions are to getting to each other, which means their y values, the values they're generating, are getting really, really, really close. And we know that when we divide numbers by each other that are really, really close, we get numbers that are really, really close to 1. So because we are taking the limit, which says, yes, you can make it to infinity, that means that these graphs actually eventually make it to each other. Now, in reality, that can't happen because we can't make it to infinity, but limits allow us to, surpass that little problem and say, let's say we could. So that's what our definitions mean. This is actually the right end behavior model because we're approaching positive infinity. But if I take the limit of my function divided by its end behavior model, as we approach infinity, we better have a value of 1. So that's what that's all about. Okay. So now that we reviewed that, let's talk about what we think would be the right end behavior model. Okay. So this time we're going in this direction. Well, we know that exponential functions are the most powerful functions we have. Now, it's not that negative 2x isn't approaching infinity, in this case negative infinity, it is, but it's not approaching it as fast as an exponential. The exponential is going to blow it away in that case. And so we're going to switch and say that in the right direction, e to the x is more powerful, and that's why we're testing it as the end behavior model. Yeah, in a lot of cases, that's the most difficult decision you need to make, is is which function should I use in the left direction and the right direction. And it really goes back to how well you know your functions from Unit 1 when we studied all those parent functions. It's really your responsibility at this point to know that. And go back to Unit 1 and review, pages 10, 11, 12, 13. Or flip to like page 67. Now, that's a guess, but it would be right around there. And there was a picture, there was a page with like 12 different graphs of all the parent functions, and get their shapes down because we really need to understand that. Now, if you can't remember what functions are more powerful than each other, we used to have that list on the classroom board, hashtag old days. And I know you don't have that anymore. So I've been working on a little document that has the list of all of our parent functions and how they relate with relative power, as well as graphs that kind of allow you to see that power. And I will try to get that out today so that you can use it as in preparation for your studies tomorrow. But the most powerful functions that we study with are definitely exponentials in this class. So here's how the algebra works once you determine what you think the end behavior model is going to be. You're always going to split the fraction, okay? And then you're always going to split the limit. And one of those limits, one of those fractions, is 100% of the time going to turn into a 1, because remember, there's two terms up top and we're dividing by one of them, so one of them is always going to turn into a 1. So the limit of 1 is 1. Now remember, we're supposed to get a limit of 1. So what that tells us is that other limit, every single time, better turn into a 0. And if we picked the more powerful function to put into the denominator, we did our job. And it should, because we understand from the studies of rational functions that we did that when the bottom of a fraction is more powerful than a top, the value of that fraction is going to get smaller and smaller and collapse to 0 the further out you go. So in the negative direction, we found that 2 to the x is much more powerful than e to the x in that direction, because the e to the x is moving towards 0. So this zeroes out, which is why the limit is, it turns into a 0. And same thing over here in the right direction towards positive infinity. The e to the x is blowing up fast in this direction, and the negative 2 is just like doo doo doo, heading down nice and slow. And so because the bottom is more powerful than the top, the value of this entire fraction, the further out we go, is going to get tinier and tinier, eventually collapsing to 0. And that's how these problems will work every single time. All of this is in your course pack. So go back and look at that structure, okay? 40. I already have these lined up at this time, right? It looks like this time we have e to the negative x, so it's going to blow up and moving in the left. Now, x squared is no slouch. It's growing pretty quick, in the left direction too. But polynomial growth, power growth will never, ever overpower exponential growth. And so e to the x is more powerful as we move to the left. And that's why we're going to use it as our end behavior model. Okay, we're going to assume that it is and divide by it. Now in the right direction, we get an e to the negative x that's collapsing, right, to 0, and an x squared that's blowing up towards infinity in that direction also. And so in the right direction, we get an end behavior model that's x squared. And that's why we're dividing by x squared. And then you can watch the work after that, but it's the same every time. We split the fraction, we split the limit. Here I split the fraction first and then split the limit. Here I split the limit and the fraction kind of simultaneously. So don't ask me why I did it slightly different order, but one of these is always going to turn into a 1, right? We divide anything by itself, it's going to turn into a 1. And the other one should turn into a 0 if we picked the more powerful function in that direction. So in this case, in this direction, in this case, x squared is more powerful in this direction. If the denominator of a fraction is more powerful than the top, the entire fraction will 0 out as we approach infinity or negative infinity. Okay, don't write a fraction and tell me it's equal to 0. That's never going to be true. But if you write the fraction and tell me that it's approaching zero as we take the limit toward that infinite direction, then yes, the limit will equal zero. That's the magic of limits, the power of limits, okay? Here's some graphs that I actually did on this one, where you can actually see, the x squared and the e to the negative x, and you can see the e to the negative x with the tables, especially being much more powerful, moving to the left direction. You can see these values um, way more powerful than x squared. 22,000, I think, is just a little bigger than 100, don't you? On the other hand, in the right direction, I compare the same values, and the e to the x's, the e to the negative x's are collapsing to zero. Look at that, 0.05, 0.02, 0.007. Those are getting tiny, whereas the good old x squareds are like, yeah, I'm going to get big still. And so that's that power that we should have learned when we analyzed all of our parent functions back in Unit 1. Now, 41 and 42 are the same business, but what we find on 42 and 41 is that when we compare, x to the natural log of x. By the way, the reason they did natural log of the absolute value of x is because we remember from studying our logarithmic functions that logarithms cannot operate on negative numbers. And so if we just did natural log of x, it would look like this, remember? Pretty weak function, approaching a vertical asymptote at zero and never hitting zero, so its domain was just 0 to infinity, not including 0. Well, we want this to have a left end behavior also. Right now it only has a right end behavior because it doesn't approach negative infinity. So by putting the absolute value signs inside, we still can't take the absolute, or the natural log of 0, but now all these negative x values turn into positive x values, and it basically allows us to mirror image our graph and observe it in both directions. So now it has both a left and a right. But it doesn't really matter because the good old fashioned boring x, the origin, y equals x, right? Da, 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 go up 1 over 1, up 1 over 1, is way more powerful in both directions than this super weak growing natural log function. One of the, it's the weakest function we have other than a constant function, that doesn't grow at all. And so in both directions, whether we're approaching negative infinity or positive infinity, x is going to overpower the natural log of x. And so this is a case where instead of choosing different functions in each direction, look at this. I say, okay, x is more powerful in the left and x is more powerful in the right. Now in your notes, what it tells you is that means we don't call x the left end behavior model or the right end behavior model. We just call it the end behavior model. It's just the end behavior model, y equals x. And what that tells us is if we graph x plus natural log of x, and we go out far enough, it's just going to look like y equals x. Now, after we make that decision, and I do think that that's the most analytical part of this process, once we make that decision, the rest is just taking the limit of the fraction, f of x over g of x, dividing by the g of x, splitting the limit, splitting the fraction, and then analyzing those limits. One of them will always turn into a 1 because we're dividing something by itself, right? So this is 1, this is 1. And the other one should always turn into a 0 because the more powerful function is in the denominator. And when we have functions that have more power in the bottom than the top, if we go towards infinity or negative infinity, they're going to turn into zeros. I know I've now said that like 29 times today, and a lot of you guys are like, just shut up, but it's such an important concept. I am going to beat it like a drum. And then, of course, you can look at 42 in your course pack. X squared is always more powerful than sine of the x. I mean, here's here's your x squared. Here's your sine of the x. X squared is a parabola that we know has decent growth in both directions. Sine of x has no growth. Sine of x is actually as weak as a constant value. Like if I had a line that was like y equals 3, well, it looks like I just drew y equals 3. How about that? It would be just as weak as sine of x. Well, sine of x would be just as weak as it because it's bounded. It has an upper bound and a lower bound. So sine of x never gets smaller than -1 and bigger than +1. It's bounded. So it's just as weak as a constant function as far as we're concerned. Okay. So that means that x squared is more powerful in both directions yet again. And so it's the end behavior model for x squared plus sine of x. In fact, we wouldn't call it left end or right end. We would just say it's the end behavior model. And I will work this one out for you just so you know. I know you have the pictures in your thing, but to see it actually being done in real time, I think is worthwhile. I know a lot of you guys don't need to see it, so you could either fast forward to the last couple problems or just shut down the video. But I'm going to work this one out. All right. So we've already decided that that y equals x squared is more powerful in both directions than y equals sine of x. We just had that discussion. So I'm gonna assume that this is my end behavior model in both directions. I hope that you guys are okay with that. So we are going to move this up a little bit. We're going to set up two different checks. We're going to check up the left check and the right check to show how this works. And in the left check, we're going to take the limit as x goes towards negative infinity of the original function f of x, which was x squared plus sine of x, divided by what we believe is the more powerful function, which will dictate the end behavior, which we said was x squared. So I think technically the way that this should work out is you should probably keep one single limit and split that fraction first. Okay, and then once you do that, then you can split the limit. But what I'm going to allow you to do on these problems is I'm going to allow you to split the fraction and the limit kind of simultaneously. So I would actually let you go straight from, whoops, let's back up just a little bit there. I would actually let you go from the first step up there, the original check once we do our division, to this point right here directly. So I will let you skip the step of work and kind of split the fraction and the limit simultaneously, since they are very similar in process. Now, after that, we can do some evaluation. So x squared over x squared is -1. Don't just, or +1. Don't go straight to 1 here, because the way that you have it right now, we'd have to plug in negative infinity to evaluate this, but we're not allowed to do that. We're not allowed to plug in negative infinity. So what you really need to do is cancel first. Once it becomes a constant, then the limit of a constant is the constant itself. Now, on the other hand, this guy right here, you could pretty much do right now. We know that the bottom is much more powerful than the top as we move in both directions, but specifically here to the left. And so this whole thing is going to zero out. And that's all you have to do. There's really no work to show. You can't plug infinity or negative infinity into these functions. You just have to understand that if I'm looking at end behavior and going way out this way or way out this way, the fraction with a more powerful denominator is going to become a smaller fraction and a smaller fraction and just disintegrate into 0. Okay, so that's it. The limit of 1 is 1. Doesn't matter if you're going to infinity or to 2. The limit of a constant is itself, and that's your check. We just showed that the limit of um, as we went to negative infinity of f of x, the original function, over g of x, the end behavior model, is 1, verifying that g of x is the end behavior model for that function. Okay. I'm actually, I guess I'm not going to do the positive infinity direction because it looks exactly the same. I mean, it really is a carbon copy. But you know what I will do is I will show you how this really works. Okay, so let's take a look really quickly at our graphing calculator, and I'm going to start with a fresh equation. Actually, I guess I could just clear this equation out, and I'm going to go ahead and type in um, our our graph. Okay, the original function was it's just x squared plus the sine of x. And you probably do want to check that you're in radian mode, and I am. So I'm good to go. So that's what that function looks like. Now, when you really think of it, it just looks like oh, apparently it went into F2. That's kind of weird. I really don't want the sine graph there. I'll turn it off. All right. Now it's, apparently I have no idea what I'm doing. Some of you guys probably knew that a long time ago. So I appreciate your support. All right. Now I only have one function. No, now I have no functions. That's probably because I still have it turned off. Oh, turn it on. All right. So it looks just pretty much like x squared. It really does, except that it doesn't start at 0, does it? The vertex isn't at 0. It's a little bit off shifted. And if you really pay attention, it's not quite as smooth as you would normally see. It's a little bit shakier in here if you really zoomed in. And that's the effect of sine of x. There will always be that small effect. But the point here is that the further out we go, the less that effect becomes. So what I'm going to do now is I'm going to go ahead and put in the end behavior model x squared. And what we're going to see is that the more I go out, the closer these things become to each other. Now, I don't have to really go out as much as I probably need to go up. So let's adjust the window here and go quite a bit further up. Maybe, you know, let's go to 120. I don't really need to go down at all. So I'll just leave it like that, okay? Yep, I just did the x values, not the y values. I should really start using some kind of editing software where I could fix that without having to go back and redo the entire video. You know what I mean? All right. I think we finally got what I was trying to get a long time ago. Whoa, look at that. So um, in this area, you can still see there's definitely some variation. You can see where the blue and the red lines are not exactly the same. And it's kind of interesting that they kind of weave back and forth across each other because that sine value is making it just a little bit bigger, then a little bit smaller, then a little bit bigger. But by the time we get like, out in this area, you don't really see that weaving anymore, do you? Because the x squared values are getting so much bigger than the sine x values that the difference is minuscule, and so the difference in y values is within very very small amounts. So that's the power of that end behavior is if you go out far enough, the functions basically become each other. All right, so that was a long bit on end behavior models, but this is always one of the harder, um, more abstract pieces for folks. So I hope that helped. The last couple questions um, were based on just these piecewise functions. And I guess I know the answers are in your notes, but I think I missed them. Oh, by the way, 43 through 46, you didn't really have to worry about. But 47 and 48, they're the answers. Um, and then why are those the answers? Well, I guess we could look at one of them. Nobody really asked either one, so I'll just pick one at random. 47 here. So it looks like at 0, we kind of have a break point where we do a piecewise swap. Now before that, 1 over x is just the inverse function, not the inverse function, the reciprocal function, right? One of our parent functions, the parent um, of all the rational functions, and it actually looks like this. So this is what it looks like. Okay, what's again? If you know your parent functions from early on, you're in great shape. Now remember, not only did um, this have the do rational functions have a vertical asymptote at 0, they also have a horizontal asymptote at 0. So here you go. And that's going to help us answer some of these questions. Now, on the other hand, we just have a constant function of 1. So at 1, I'm just going to go, and it looks like it is defined at 1. So this would be a closed circle. Now, as far as limits are concerned, they don't really care about that. But so that's what this piecewise function would look like, okay? So now we can answer the questions. Part A. What is the limit of f of x as x approaches negative infinity? And what we see is that we're approaching a horizontal asymptote at 0. So this limit is going to have a value of 0, okay? What is the limit of f of x as x approaches positive infinity? So that's the right end behavior. And it looks to me like we're on a horizontal line, which you could call a horizontal asymptote. I mean, it passes the test. If you approach infinity and your function is approaching a constant value, even if it is the constant value, right, then it's a horizontal asymptote. So this graph actually does have 2 horizontal asymptotes, 0 to the left and 1 to the right. And so it does have a horizontal asymptote at 1 moving to the, oh, I'm sorry, negative 1. I didn't even notice that, so I'll move it down. Now we're talking, right? All right. So that this is end behavior right here. You know, this is when you're approaching infinity and you're talking about infinity. It's just all about end behavior. So now we're going to switch, and we'll talk about approaching 0 from the left and from the right. So when I approach 0 from the left, so approach 0 from the left, right? X. What am I doing? So I'm coming in, the x values are getting closer to 0, and as I get close to 0 from the left, I start dipping down that asymptote. So even though infinity is not technically a limit, we describe the behavior around vertical asymptotes with infinity, and so I would definitely call that negative infinity for that limit, okay? Technically the limit doesn't exist, but for our sake, we're going to give it direction, so we'll say it's approaching negative infinity. Now, on the other side, you're like, well, that means we're approaching positive infinity, right? Well, if it was a full rational function, that's true. But from the right, remember, we have a different function that's just a horizontal line at negative 1. So as I come into 0 from the right, I'm just, once again, hanging at negative 1. And so that's where those answers come from, 0, negative 1, infinity, and negative 1 again. And you can see that matches up with what we got. So that's what you do on those problems. You just kind of graph them out. So this is already longer than I intended because I spent really a lot of time with the end behavior models. Hopefully that does pay off for you, though. if you're done, then go ahead and you can cash out. But if you do want a little more information on 43 through 46, I'll give you like an extra 5 minutes right now. Okay, so here's the idea behind it. Okay, there's a very intimate relationship between 0 and infinity. They are not what we would call reciprocals, because infinity is not a real number, and you can't take a reciprocal of 0 because that creates an undefined value. But they're as close to opposites as you can really get. 0 is nothing. Infinity is everything, right? And we learned in trigonometry when we were doing the table, and you probably saw this in algebra before that, but when we were going around the unit circle and we did our first tangent 0 and got 0 over 1, we're like, well, we're dividing um, into 0, and that's going to have a value of 0, because how many ones fit into 0? None. If I had a bucket that had 0 room left in it and I tried to put 1 ounce of water in, or 1 gallon, or 1 whatever, it's not going to fit. Now on the other hand, if I ask how many zeros fit into 1, that would be like I have a bucket that has 1 gallon of room left and I'm putting 0 gallons in. How long is it going to take to fill? Well, it's never going to fill, right? I'm putting 0 in, it's going to remain empty forever. So infinitely many zeros fit into 1. So 0 and infinity really do have a type of reciprocal relationship, even though they aren't really reciprocals. And it's that premise that this strategy is based on, okay? This is, out of the book that we're pulling all your problems from. They have a little section where they talk about seeing limits as x goes towards plus or minus infinity, because we can't really graph. We can't graph out there. We can draw the graph and put an arrow on it and say, yeah, it's going towards infinity. But even if you scale your graph so that the right edge of your graph is 1,000,000,000, that's still not anywhere near infinity. Okay, so what this says is we can investigate end behavior approaching plus or minus infinity. Okay, if f of x, we want to examine that at its ends. Instead, I can take kind of that reciprocal-ish value of infinity and rather look as x approaches 0. Now, the trade-off is that if I do that, I can't do it with x. I have to do it with the reciprocal value of x, 1 over x. That's the strategy here. And it's not important enough that we need to worry about it right now, especially in this remote situation. But here's the example that goes with their little strategy there. What is the limit of sine of 1 over x as x approaches infinity? Okay, positive infinity. Well, that's a graph we're not that familiar with. We actually did look at it at the beginning of the semester, but you probably don't even remember it or remember why we looked at it, okay? But here's their strategy in motion. Instead of looking at the limit of sine of 1 over x as we approach infinity, why don't we look at the sine of the reciprocal of 1 over x, which would just be x, okay? S, instead of x approaching infinity, x approaches 0. Now you do have to be careful about how you're approaching 0. In this case, we're approaching 0 just from the right, because this was positive infinity, so this has to be 0 from the positive side. Okay, well then it becomes a very, very simple problem, because we know sine of x very well, and we know that as we approach 0 here, right, as we come into 0, that our sine graph has a height that is also approaching 0. The closer that I get to 0 with sine, the closer that the y value comes to 0. And that's what they're saying right here. This was a little bit too ugly for us to look at. So why don't we look at this? Because this is something we know very well. they're going to have the same value because of the relationship between 0 and infinity. Okay? Now, if this was a calculator problem, then this isn't hard to do the original problem at all, because I can graph sine of 1 over x and say, I wonder what's happening as I go towards infinity. Oh, look, it looks like it's going down towards the horizontal asymptote at 0. Awesome. And so I would get the same exact answer. But if you didn't have a calculator, or if it was a really weird type of situation, this strategy can be quite helpful. And this is the type of relationship between 0 and infinity that's really going to pay off if you understand it in calculus. Okay. Now, just as a reminder, where did we see this crazy graph before? After we had defined, this was like the first week of class, after we had defined removable discontinuities and infinite discontinuities and jump discontinuities, there was one weird fourth type of discontinuity that I told you needed to know about, but that we weren't going to analyze it, and it was called a oscillating discontinuity. And so because 1 over x is a fraction that, as we put really, really tiny numbers in there approaching 0, is going to get super, super big, making sine oscillate ridiculously fast, infinitely fast. Its oscillations become utterly chaotic here towards the middle, and that was absolutely pointless. Let's try that again. And so it's called the oscillating discontinuity. Okay, that's where you'd seen that before. So hopefully that explanation helps you understand a little bit about those. Now, if you look at some of the problems, like I have 43 worked out for you here, instead of doing x times e to the x, which is a medium function multiplied by a crazy powerful function, and if you could graph it, I mean, you could probably figure it out really easily, right? In fact, this is the graph right here of e to the x multiplied by x as we approach infinity. It looks like we're just shooting through the roof. But if I take the reciprocal of x, 1 over x, and put it in for x, so there's your 1 over x, and then put it in for x with e, so there's e to the 1 over x, I get a totally different graph. I get this graph right here. But now we're not looking at it, the graph as it goes to infinity. We're looking at it as it approaches 0 from the right. And sure enough, 0 is x equals 0 is a vertical asymptote, and we're approaching positive infinity. So we get the exact same answer in that manner. Okay. Now, what's going on as I approach, negative infinity with this graph right here? Well, it looks like, and this looks like a totally different graph than this, but these are really the same. It's just that this one is at a much smaller scale, so we see this little loop-de-loop underneath before it starts coming back up. We don't see that on here, but it turns out that as we move towards negative infinity, it appears that we are approaching a horizontal asymptote at 0. So it looks like we're going to hit a 0. Well, let's test our strategy. You ready? If I put a 1 over x in for x here and here, so this and this get replaced by this and this, right? And then instead of looking as we approach negative infinity, I look as we approach 0 from the left. Okay, let's see what happens here. Looks like our graph is coming down and then starts back up, and oh, look at that, it's heading right towards 0, which is the answer we got, doing it the original way also. So that's how you could do these. And notice that you definitely would want to be doing these with a graphing calculator. It even says use the graphs, right, of these. But hopefully that helps a little bit. And good luck on your quiz tomorrow. Let me know if you need any help in our help session this afternoon. Adios.